First, I would like to differentiate between cognitive and metacognitive skills. Cognitive skills involve strategies such as visual strategies, which may involve circling words or underlying key pieces of a word problem. This helps the student analyze the demand and realize the task that they need to complete, whether it's joining, separating, changing, or comparing values. Metacognitive skills involve the ability to plan, monitor, and modify approaches when problem solving. When these strategies are combined through explicit instruction, they have been found to promote student skill acquisition and increase their understanding of problem solving. The materials necessary for this intervention are commonly found around the classroom. All that's needed are story problem cards, displaying a poster with the 7 cognitive strategy steps, pencils, papers, and of course, our self-monitoring worksheets. We should always pair this intervention closely with providing the student with their performance feedback, praising them, and encouraging them. And for students who may need additional incentives, this can easily be paired with a reinforcement schedule that provides the student with a point for each assignment correct answer, as well as additional points that they can earn for completing their checklist.
Solving an advanced math problem independently requires the coordination of different skills. The student must be able to implement specific steps for problem solving, which are the cognitive strategy steps, as well as having the required metacognitive skills required for monitoring the process of problem solving. The student is taught a 7-step process for solving a math word problem, which is the cognitive strategy that includes Step 1, read the problem. When the students read the problem carefully, noticing and attempting to clear up any confusions, for instance, the unknown vocabulary terms. The Step 2 is paraphrase the problem when the student restates the problem in his or her own words. Step 3 is draw the problem when the student creates a drawing of the problem having a visual representation of the word problem. Step 4 is creating a plan. The student decides on the best way to solve the problem and develops a plan to do so. Step 5, predict, estimate the answer. The student estimates what the answer to the problem will be. The students may compute a quick approximation of the answer using rounding or other shortcuts. Step 6, compute. The students follows the plan developed earlier to compute the answer to the problem. And Step 7 is checking the answer. The student checks the calculation for each step of the problem. The metacognitive component of the intervention is a 3-part routine that follows a sequence of say, ask, and check for each of the 7 problem-solving cognitive steps from the previous slide. The student first self-instructs by stating or saying the purpose of the step. The student next self-questions by asking what he or she intends to do to complete the step. The student concludes the step by self-monitoring or checking the successful completion of the step. While the say, ask, check sequence is repeated across all 7 problem-solving steps, the actual content of the student's self-coaching comments changes across the steps.
Here we have included an example of a student fidelity checklist. As you can see, this intervention has been summed up as a say, ask, check model. Before the student begins their assignment, they should read the steps, self-identify if they believe they can complete the steps successfully, and after each problem, they should complete the checklist identifying whether or not they were successful in completing that step. If they weren't able to be successful, they should leave their original work and complete the say, ask, check model again. Upon completing their assignment, they should additionally complete a self-corrections checklist. This is an example of a self-corrections checklist that will be completed upon ending an assignment for each missed question that a student had. This will have them look at each individual missed question and complete the checklist, underlining any numbers and circling key pieces, checking whether or not they were able to read their written work. Did they line their numbers up correctly? And then they recheck their answers. I've included an additional example in our appendix, which includes an additional column for the student to identify the problem number. This also allows for teachers to make notes on the student's academic performance, which can serve as a tool for explicit instruction and progress monitoring. As mentioned previously, students gain the most through close teacher support when combining the 7-step cognitive strategy we see here with the 3-step metacognitive model of Say, Ask, Check. By using explicit instruction to teach these cognitive and metacognitive strategies, checklists promote implementation with fidelity. Fidelity is crucial for student success. Implementation with the checklists allows the teacher to assess their students' foundational skills. It creates opportunities for the student to engage in appropriate problem-solving strategies. And it also ensures the student is experiencing an adequate rate of success by offering frequent performance feedback that keeps them motivated and guides their learning in a way that promotes deeper understanding of problem-solving strategies. A few implementation tips are to offer prompt performance feedback to the student in combination with this intervention. For students who may need extra incentives, consider pairing this with a reinforcement checklist. And when fading the intervention, do so gradually when the student begins to meet their goals.
So today we will model for you how we will use the math problem solving strategies to solve word problems, and this strategy has 7 steps. The first step is read the problem. There were 15 birds flying in the sky. 3 were yellow, 4 were red, and the rest were blue. How many birds were blue? So the first question that I ask myself if I understood the problem. If I understood the problem, I go to the second step, which is paraphrase the problem, which means to say the problem in my own words. So what I know from this problem is there are some birds, they are flying, and some are yellow, some are red, but we don't know how many are blue. Okay. Then the third step is to draw the problem. So to draw the problem, I will draw 3 yellow birds. So I just imagine that those circles are birds, right? 3 yellow birds, 4 are red, and I do not know how many are blue, but I know that in all are 15, okay? So I will create a plan to solve the problem. So what I'm going to do, I'll write how many are yellow, 3, 4 were red, and some were blue that I don't know how many, and in all I will have 15. So the fifth step is to predict the answer. Since in all are 15, I know that my blue ones will be less than 15. So I will, from those 15, I will take away the 3 yellow and the 4 red, and I will find out that the blue ones are 8. So I can draw 8, 5, 6, 7, 8 blue birds. And the last step is check the answer. So how do I check the answer? Well, if I know that I have 3 yellow, 4 red, and 8 blue, if I add all together, I should have 15. So 3 plus 4 equal with 7, 7 plus 8 equal 15. So I solved the problem. So those are the steps that I have to follow to solve our word problem. Now you can solve the next story problem using those steps, and the checklist in here to see if to check for each step, to self-monitor yourself that you're using the steps.
Okay.
So first you have to
Read the problem. Okay. Timmy picked flowers with only 5 petals. If he picked 4 flowers, how many total petals did Timmy collect? Okay?
So you read the problem and you ask yourself, did you understand the problem?
Yes, I think so.
What's the next step?
To paraphrase the problem.
Okay, which means to tell the problem in your own words.
So Timmy picked some flowers they were 5-petaled flowers, and he had 4 of them, but I don't know how many petals there were total on all of these flowers.
Good job. The next step is
to draw the problem.
All right, so go ahead and draw the problem.
Yay, okay. All right, so he picked
4 flowers with 5 petals each.
Okay, I'm gonna just draw 4 flowers.
All right.
And they each have 5 petals.
That's correct. Okay, the next step is to create a plan to solve the problem. So you can write how many petals you have under each flower.
Okay, so on each flower I have 5, so
right.
I'll write 5 under each flower.
Right.
And then I can add them up?
Yes. Now you check this. Now the next step is to estimate the answer. Will you have more petals or less petals?
I will have more than 5 petals.
Alright, very good. Now you compute the answer.
Okay, 5 plus 5 is 10, plus 5 is 15, plus 5 is 20 petals on Timmy's flowers.
Very good. So now you check your answer. If you have 20 petals and 4 flowers, how many petals will each flower have?
Each flower should have 5 petals.
That's right. Very good. So this is the strategy of solving word.
The research shows that when paired with cognitive strategies, metacognitive strategies have been shown to increase the understanding and ability of students with mathematics learning difficulties and disabilities to solve mathematical problems. In his research, Babakani used the cognitive and metacognitive strategies to measure the effects on verbal math problem-solving performance of students that have verbal math problem-solving difficulties. The subjects of the studies were 60 fourth grade students that had difficulties with math problem solving. The students were divided into groups: the experimental group, 15 boys and 15 girls, and the control group, 15 boys and 15 girls. All subjects were matched in experimental and control groups on intelligence, having an IQ range between 95 to 115, average age 9 years and 6 months to 10 years and 6 months, and average math performance. The experimental and control group was given a pre-test and after that the experimental students received cognitive and metacognitive strategies instruction of 16 weeks of 45 minutes in 2 months during the school hours. After that they were given a post-test to measure the verbal math problem-solving performances in each group. Teaching of cognitive and metacognitive strategies
self-instructional procedure significantly improved performance of experimental group in both gender. The researcher compared the mean of the performance between the experimental and the control group. The comparison in both pre-test and post-test of problem solving indicated that the performance of the two groups increased in post-test versus the results in the pre-test. However, the mean of the experimental group increased up to 4.33, while in control group increased only 2.3. This happened while there was no significant difference between the two in the pre-test. There were no significant differences between boys and girls in either applying the strategies or effectiveness of teaching. The research results can be viewed in this graph as well, where you can see that the experimental and control group, which is with blue, had the same results, while after the post-test, you can see the experimental group had higher scores than the control group. As well as in the second graph, you can see the difference between pre-test and post-test for experimental and control group. Those are our references, and thank you for watching our presentation.